Good afternoon, Algebra 2, or good morning or good evening, depending on when you're watching this video. Today we're going to start off with our 7.1-7.2 graphing material. We're going to combine both of these sections today, dealing with growth and decay of functions, dealing with just the graphing aspects. That way you can compare and contrast the difference between the two of them. First thing we're going to talk about is the definition of an exponential function. Exponential function will always be written in the form that you see on the notes. Y equals a times b to the power of x. X will always be an exponent when we're talking about exponential functions, hence the name. We have an a. A will always be the number in front. It cannot be a zero, otherwise the function will disappear. And a will also act like the slope. So your general rules for slope will remain for a. If it's negative, it's going to flip it. Okay, the higher the slope, the faster it moves. The slower the number, the slower it moves. That a can be any number except for 0. B we're going to call the base. And we're going to say that name quite a lot throughout this whole chapter. B will always be attached to the x. That's how you will know when you're talking about the base. It will always be attached to that power of x. X is the variable, yes, but it's going to be the exponent, and that's why it's special for this section. You're not used to seeing x as the exponent, but that is what we're going to be dealing with now. So this is our general definition, our general form for an exponential function. So anytime you see that x is a power, make sure you recognize that that is the exponential function. Now, a little review to make sure we understand the concepts of powers. First, on the left side, we've got our 2's and we've got our powers. 2 to the first power. Hopefully by now we all know and recognize that 2 to the first power is just 2. 2 squared, or 2 times 2, would be 4. 2 cubed, or 2 times 2 times 2, would be 8. 2 to the fourth, or 2 times 2 times 2 times 2, would be 16. And then 2 to the fifth, 5 times, would be 32. If we took the same concept, but we took it towards fractions, and we used our examples of 1/2, so let's see what we would come up with. 1/2 to the first power is 1/2. 1/2 squared would be 1 squared and 2 squared. So 1/2 squared would be 1 over 4. 1/2 cubed would be 1 cubed and 2 cubed. So 1/2 cubed would be 1 over 8. Therefore, 1/2 to the 4 would be 1 over 16. When we look at the relations that we have between these two, and we look at the 2's on the left, we notice that as the power goes up, as the power goes from 1 to 2 to 3 to 4 to 5, the answers in return also are increasing. These are our growth equations, okay? And that's going to be when that b, that number that's attached to that x, is greater than 1. And for this example, that b was 2. When we look at the opposite side and we look at our 1/2, and the same thing is happening with our powers. We have 1, 2, 3, 4. But this time when we look at our answers are not increasing. This time our answers are decreasing. Those fractions are getting smaller and smaller and smaller. So in this case, when our b was 1/2, we were actually decreasing or decaying. And that decreasing or decaying functions are going to be when b is between 0 and 1. So the concept we need to get from this slide is that if b is greater than 1, we're going to have a growth function. And if b is between 0 and 1, we're going to have a decaying function. And that is going to tell us what the function looks like when we're taking it and we're graphing it. So our first two examples. We got our y equals a times b to the x up at the top. We got to remember that we're really concerned with this b, this base. So when I look at my first example, a is greater than 0, a is a positive 2, and b is a 1/3. So b is between 0 and 1. And what we just said a second ago, if b is between 0 and 1, we have to know that that means this is going to be descending. This is going to be decreasing. And we call that exponential decay. On the opposite side, a is less than 0, but b, remember b is what we're concerned with. This b is greater than 1. So since that b is greater than 1, this function is going to be ascending or growing. Because remember, when we said that b was greater than 1, those answers were going to get bigger and bigger and bigger and bigger. So that will be a growth function. Now, the next thing I want you to do is take these two functions, type them in your calculator, and let's see what they actually look like on a graph. Okay, so we take this first one, 2 times 1/3 to a power of x. When we take this and we graph it in our calculator, we get a function that looks similar to what I've drawn on my graph. Now, let's talk about what this is. We said this is a decaying function. So when we see this function, we notice how it starts up high and it's decreasing down. It is slowly, slowly, slowly getting smaller and smaller and smaller right here at the end. But what we need to recognize is that this line down here will never cross the x-axis. And the reason it'll never cross the x-axis is because when we plug in numbers here, this is never going to get lower than 0. Okay, so this is never going to cross the x-axis. That is going to come in play when we talk about an asymptote. Whether or not you remember an asymptote from Algebra 1, an asymptote is a line that a function approaches but never crosses. So when I'm looking at this graph, this axis right here, and I'm going to draw a dotted line, would be considered my asymptote. This graph is going to get closer and closer and closer to that line, but it's never actually going to cross it. It's going to look like it's just running right next to it. Those asymptotes are always going to be labeled with a y. So for this equation, my asymptote is the axis, so my asymptote is going to be y equals 0. My domain and my range. We've started talking about domain and range, so hopefully this is a review for most of us. Domain references my x's, my range references my y's. So when I'm looking across my x-axis, there's two things I need to notice. I've got two arrows. This arrow up here on the top is telling me that this line is going to keep going left and left and left and left and left, and it's never going to stop. This arrow over here down on the bottom is facing the right, and it is never going to stop. So my domain, or my x's, continues all the way from the left, or negative infinity, all the way to the right, which is positive infinity. And if you remember from the last chapter, infinities always have those parentheses. Our range references our y's, and when we look at this graph, we notice what we talked about with the asymptote, that we have a line right here, this asymptote, and we said it's never going to cross this line. And if it's never going to cross this line, we know that there is no function down here on the bottom. So since there's no function down here on the bottom, that means the first y that we have is 0. That's the first option that we have. And we notice this arrow up on the top is facing up. Arrows means it's never going to stop. So we're going all the way up to positive infinity. The difference from what we did before is this asymptote, though. This asymptote, remember we said, means it can never touch that line. And since it can never touch that line, we don't have a bracket on this 0. Since it can never touch it, we have a parentheses. So my range would be parentheses 0, comma, to positive infinity. My y-intercept, a little hint for how to find your y-intercept. Y-intercepts are always where x equals 0, always. So all you have to do is plug in 0 and then see what you come up with. So for this question, when I plug in 0, I have 2 times 1/3 to a power of 0. Well, hopefully we remember from the last couple chapters, anytime you have a power of 0, it cancels and just becomes 1. So this is 2 times 1, which is 2. So my y-intercept, as you can tell on my graph right here, is at 0, 2. Now let's look at the same concept for this second example. We have 1/2 times 4 to a power of x. So if I'm looking at this question and I'm looking at the graph, I've got a couple things that I need to find. Okay, first thing, type it in our calculator. When we type it in our calculator, we come up with a function similar to this. Now, if you notice the difference between this graph and the first graph was a decay graph, hence the reason it was coming down towards the axis. The second one is a growth graph. That is the reason that we're starting at the axis and we are growing up. That's why it's called a growth function. Now, let's look at the same concept as what we had before. Asymptote. If we look at our graph, we are flattening out on this axis. So again, I'm going to draw my dotted line right here on my axis. That's where I'm flattening out. Therefore, since I'm on the axis, my asymptote is y equals 0. My domain, it's going to keep going to the left, as that arrow shows me here. This arrow up here is slowly but surely going to keep going to the right. So therefore, my domain, again, is -infinity to +infinity. My range, when I'm referencing, again, there's nothing down here on the bottom. The first thing that I have is right here on my asymptote, which is 0. And then this arrow is going to keep heading up. So my range is 0 to +infinity. But yet again, since this 0 is an asymptote, and the definition of asymptote means it cannot ever touch or cross, the 0 has a parenthesis. Y-intercept, remember, that's when x is 0, so we plug it in. We get 1/2 times 4 to the 0. Again, anything to a 0 power is 1, so we have 1/2 times 1. So my y-intercept will be at 1/2. And again, if we look at our picture, let me fix my pointer. If we look at our picture right here, our intercept is at 0, 1/2. Now, let's look at the next two. Same concept, but a little bit faster this time. Only difference between these questions is now we have a negative, so all that's going to change is the direction of our graph. So if I look at this first one, again, remember the key is to look at this b. My b for this first question is right here. Since my b is a 1/2, that means it will be descending and it will be a decaying question. When I look at the second one, again, it's negative, but the b itself is 3. So since 3 is greater than 1, this one is going to be ascending, and it's going to be a growth equation. Okay, again, start by plugging them in. When we plug this first one in, we get a graph similar to this. Mine's a little off, but that's all right. If I were to take this graph and to flip it, it would look like this. And if you notice, the reflection across the axis is where this negative is coming into play. So when you say decay and you look at what we have, it doesn't look like decay, but when you flip it, this is going down. This is a decaying function, but that negative is taken it and flipped it across the axis. So now we don't have a function up on the top. Our function is down on the opposite side of the x-axis. So our domain hasn't changed. We're still going left. We're still going right. My range is now backwards since I flipped on the axis. My range, I'm now going down, but I'm stopping right here on my asymptote. So my range is now backwards. I'm going down to -infinity, and I'm stopping at 0, and there's nothing above 0. My asymptote is still that axis, so my asymptote is still y equals 0. And my y-intercept, again, plug in 0, so I get -1/2 times 1/2 to a power of 0. That, again, is still 1, so my asymptote should cross at -1/2. And this is where I said my graph is a little off, but we should cross right there at -1/2. So my intercept is 0, -1/2. I will continue this on to my next video.